In today's lesson, we're going to look at polynomial functions of higher degrees. So we know some basic polynomials like linear equations and quadratic equations are polynomials. But now we're going to look at higher powers and what our graph looks like. And to help us this, the three main things we're going to learn in today's lesson is we're going to learn something called the leading coefficient test. Now, the leading coefficient test is going to let us determine the end behaviors of a graph, or basically what's happening at the very extremes of our graph, when x is extremely small or when x is extremely large. And that's going to help us translate that into a nice picture of what our function looks like. And then we're going to review how to find our zeros of the polynomial function. We're going to focus on real zeros. And then we're going to use that to sketch our graphs. And last but not least, we're going to learn something called the intermediate value theorem, and that's going to help us to locate zeros of polynomial functions. Now, this is just an introduction to intermediate value theorem. If you move on to calculus, a lot of what we're talking about today you will see in the first unit of calculus. It just goes a little bit more in depth. So mainly I'm introducing terminology and information here, and then you'll learn more techniques of how to do it if you move up in later math courses. So first thing, let's get a little definition of polynomials. What is a polynomial? Since we're going to be using it for this entire unit, we need to know what it is. So let n be a non-negative integer. Now remember, integers are positive or negative whole numbers like 1, 2, 3, 4, 5. So in this case, non-negative integer means 0, 1, 2, 3, 4, 5 is what I'm talking about there, up, etc. And let a sub n minus 1, a sub all the way down to a sub 2, a sub 1, a sub 0 be, which is the a represents your coefficients, the numbers in front of the x in the expression. I'm going to let them be real numbers. Okay. And pretty much up to now, all the numbers you've worked with have been real numbers. Only if you have an imaginary unit is it a real number, not a real number. With a sub n not equal to 0, so the leading term can't be 0, a leading coefficient cannot be 0, then the function f of x is equal to a sub n, so that's the number that goes with the x raised to the n power. That's what that means, a sub n. And then adding my next term, we'll call it a sub n minus 1, because that's going with the x raised to the n minus 1 power, all the way down, however many terms we need, until we get a sub 2 x squared plus a sub 1 x to the first, and then a sub 0, and then x to the 0 is just 1, so we don't write it. Okay, this is called a polynomial function of x. And we just call it polynomial for short. And this is a polynomial with degree n. So the degree of the polynomial is determined by the highest power of the x. So the x raised to the highest power is your degree of the polynomial. Okay, in this section we're going to study the basic features of the polynomial function. So there's two main characteristics that help us determine if the graph is a polynomial or not a polynomial. And these are the two that we're going to focus on in this course. So the first feature is that the graph of the polynomial functions are always continuous. Now, for our purpose, what does continuous mean? Well, continuous basically means, in terms of the graph, that the graph of the function has no breaks, holes, or gaps in it. Okay, so if I could draw the graph without ever having to raise my pencil to go over some value, then it's continuous. So for example, here I can start and I can trace the entire graph without ever raising my pen. So that tells me that this right here is a continuous graph. Now where on this other side, I can trace it, but when I get here, I have a problem. In order to start this next piece, I have to pick up my pencil and start drawing it. Go back and start drawing it. And so I had to pick up my pencil. So right here is what we call a break. And you notice there's an open circle at this end. Okay, that open circle represents a hole in our graph. So this one has a break, a hole. A gap usually looks something like You have your function here, then you start over here. So you have some spots that are blank on the x-axis as well. So this right here will represent, is what I'm calling a gap. Okay. So this one has a hoe and a break, so it is not continuous. Now the word we use for not continuous is discontinuous. So we'd say that this function is discontinuous. Now since it's discontinuous, it cannot be a polynomial. But this one is continuous, so it could be a polynomial, but we don't know for sure. We have to test the next characteristic. And the second feature of graphs of polynomial functions that they all have in common is they have only smooth, rounded turns. So all the turns are smooth and rounded. So again, this one is continuous, so I can draw all the way around as I want. But notice the second graph is also continuous. So both of these graphs here are continuous. But if I notice every one of my turns on this first graph, look at those turns. They're nice and curved. You have a nice curved graph. They're smooth, they're rounded, no sharp turns. So this represents a polynomial. It has both characteristics, continuous, and all the turns are smooth and rounded. Whereas this one might be continuous, but this right here is a sharp turn or a point in the graph. Okay, this is not a polynomial. Those are our two characteristics of graphs to make them polynomials. In fact, this is an absolute value graph, as we learned in our last unit, so it's obviously not a polynomial. Now that we know by looking at the graph if it's a polynomial or not, let's talk about some of the features of a polynomial function. And the feature we're going to talk about is what's happening at the extreme ends of our graph. Okay, so if we could narrow down these long polynomials with lots of different terms, you know, into just the simplest equation possible, that would be narrowing it down. Any polynomial function that has the simplest graphs are called monomial. Monomials. Now, monomials has mono in here. Now, mono, remember, is a term that means for one. So these have one term. So they're functions that only have one term. So back up here to our polynomial thing. Monomials will only have this first term here. All the other ones would be, these coefficients are all zero, so they all disappear. We're only looking at this term that has a single term, y equals some term raised x to some power. Okay. Now, of these polynomials in this form, so that's going to be in the form of f of x is equal to a of n x to the n. So it's going to be in this form, where n is a integer greater than 0. Okay. The following characteristics describe the end behaviors of the graph. If n is an even number, the graph will be similar to the graph of y equals x squared that we learned in our last unit. Remember, y equals x squared looks like this. Okay, and so the ends of these graphs will be going in the same direction. If n is an odd number, the graph will be similar to the graph of y equals x cubed, and they will be going in opposite directions. And more importantly, the greater the value of n, the flatter the graph is near the origin. So here I'm going to match I have graphed in the red, blue, and green here the three equations: y equals x squared, y equals x cubed to the fourth, and y equals x to the 10. I want to figure out which graph has to be which. So if I'm looking through this, I notice that the red graph is not very flat or toward the origin. So notice that the red graph is the least flat or toward the origin. And also it takes longer for this graph to go up. It doesn't climb as steeply as the others. That tells me, that this must be y equals x squared. So the red one is y equals x squared. Now, comparing to that one, If I look at my next graph and I see that it is the blue graph here, it's not quite as steep, but it's in between the other ones. It's a little flatter when it goes around the origin at 0, and it climbs a little steep, but not as steep. That's going to be y equals x to the 4th. And then our final one, which rises so fast, it's hard for us to even see it. It rises so fast, but look how flat it is toward the origin. It's getting kind of messy, so I'm going to erase that. So you can see how flat that one is getting toward the origin. It almost looks like it's flattening out completely, but if I zoomed in there, you'd see it is not flat, but it looks like it at this scale. That's going to be y equals x to the 10th. Okay, pause and try matching this graph. Figure out red, blue, or green, which one is y equals x cubed, which one's y equals x to the 5th, and which one's y equals x to the 9th. All right, y equals x to the cubed will be the red graph, this one right here. Okay, the blue graph, because it's flat but not as flat as the other one, would be x to the 5th, and then the green graph is our x to the 9th, if you're looking at this one. Now that we figured out the basic kind of shape, there are actually 4 shapes. I only did 2 because my leading coefficient was positive, but it was 1. So with the negative coefficient, we get a few more in behaviors of our graph. And that's what we're going to talk about here. It's what's happening at the ends of the graph. So, as x moves without bounds to the left, and how do we write that? Well, if we write x goes to negative infinity. So that's what x moves without bounds to the left. So I'm going to the left of my graph when x is extremely small. So I'd write x approaches negative infinity, because that's what that means. Or moves without bounds to the right, x is approaching infinity. The graph of the polynomial, and that's that standard form of the polynomial, eventually rises or falls in the following manner. So this is kind of like, this is called a leading coefficient test, and it tells us what happens at the ends of our graphs, when x is extremely small or x is extremely large. Now, if n, the degree of the polynomial, is odd, and the leading coefficient, the term in front of that x with the highest power, is positive, our graph is going to follow the shape of y equals x cubed, because x is the leading term here is 1, which is positive, and 3 is odd. Now remember from our last unit on transformations, the graph of y equals x cubed at the ends looks something like this. Now I left a blank in here because with the higher powers and the other terms that we might add, different things are going to happen in the extremis. But on these two ends, that's our graph is going to follow that same pattern, just at the end as x gets extremely large or x gets extremely small. Now how do we write this? So notice that my arrow is going down when x on my left-hand side where x is extremely small. So when x is approaching negative infinity, my function value is going to negative infinity. So you would write to describe, this describes your left end behavior. And what you'd write to describe your left end behavior is f of x goes to negative infinity as x goes to negative infinity. Now to describe your right end behavior, you would write f of x, that's the y value. Its arrow's going up, so y value is going up, so that means f of x is approaching infinity as x goes to infinity. So that entire statement there is called the right end behavior of our graph. Now, if n is odd still, but this time our coefficient is negative, it's going to follow the shape of y equals negative x cubed. So reflection across the x-axis means this end is going to be going up and this end is going to be going down. And I remember these two as odd opposites. So the ends are going to be in opposite direction. And then I have positive leading coefficient here, which is positive 1. So I'm going to end in the positive direction. And then here I got odd, so opposites my ends are going opposite direction, negative, so I got to end in the negative direction. And that's how I remember which is which. Now, how do I translate that into algebraic expression? So I'd say the left end behavior, notice my graph on the left, my left arrow is going up. So I'd say f of x is approaching infinity as x is going to negative infinity. And then to describe my right end behavior, I'd say f of x is going to negative infinity as x goes to infinity. Now let's look at when n is even. So when our degree of a polynomial is an even degree and our leading coefficient is positive, we're going to follow the shape of y equals x squared. Remember that on the ends look like this. Remember, inside could be flat or it could have extra humps. All the different things can be going on. We're just looking at the ends. So my left arrow is going up, so I'd say f of x is approaching infinity as x goes to negative infinity. My right arrow is going up, so I'd say f of x approaches infinity as x goes to infinity. Now, if n is even and my leading coefficient is negative, it's going to be the basic shape of y equals negative x squared. And so reflection across the x-axis flips it down. And so both of my graphs are going down. So even, they're going in the same direction. Okay, and if you have positive leading coefficient, they're going in the same direction as positive. And if it's even and negative, the same direction is down, negative. So the left end is going down. So I'd say f of x is going to negative infinity as x goes to negative infinity. And the right arrow is going down, so f of x is going to negative infinity as x is going to infinity. And those are your 4 answers that you're going to get for end behaviors of a graph. So let's try one. We're going to describe the end behaviors of the graph here. So first thing I got to do is notice that 8 is my highest power. So this is the binomial I'm looking at, negative 3x to x to the 8th. So x to the 8th means my degree is 8, which is an even number. Negative 3 is my leading coefficient, so that's negative. So it's going to follow the shape of an even negative, so that means we're going in the same direction but going down. And so my answer, my end behavior would be f of x approaches negative infinity as x goes to negative infinity. That gives us our left. Always write your left first. My right end behavior, my right arrow is going down as well as x is going to extremely large. So that is your answer. That would be your end behavior to this graph. And that's all the work I really need on these. All right, so for the second example, I notice my highest degree is this x is 4x to the 5th. So my degree is 5, which is an odd number. And 4 is my leading coefficient, which is positive. So odd means they go in opposite direction. They end positive. So I'm going to start down and go positive. So the left arrow goes down as x goes to negative infinity. So that's my left end behavior. And then my right arrow is going up. So f of x goes to infinity as x goes to infinity. Now notice I have to have the f of the y and the x as you have to write f of x goes to something as y goes to something. You can't just write, and I'll see this sometimes. I'll sometimes see students just write, just write this part here and think that, hey, that explains it. No, that's not enough information. That would actually be wrong and you won't receive credit. So make sure you're describing the full end behavior. Tell me which direction, left and right. All right, so the last one here. So highest degree, that's a term we're looking at, is 13, so that's odd. Negative, leading coefficient is negative 3.6, so that's negative. So opposite directions and ending at negative. So this is what our shape is on the end is going to look like. So I'd say f of x is going toward infinity. Oops, I didn't write very. As x goes toward negative infinity. And for the right end, f of x is going down, so it's negative infinity, as x is going to infinity. So that would be my end behavior for this graph. So that's called the leading coefficient test and tells us what's happening at the very extremas of our graphs. Now we're going to kind of put together, we're going to have these terminology. In this unit, I'm going to use a lot of terms. You'll hear me use terms called zeros, solutions, x-intercepts, and factors. And they are very similar. All four of these things are very similar. Almost, the process of finding them is almost identical. It's just how we write the answer that is slightly different. And so just the terminology of what we're looking at to represent what's our zero, what's versus a solution versus the x-intercept. So that's what I want to talk about a little bit in this section. So it can be shown that a polynomial function f of degree n has the following statements are true. Okay, now zeros are the points, or zeros are where the function value is equal to 0. That's why we call it zeros. F of x equals 0. So the function f has at most n real zeros. So if you have a polynomial of degree n, at most you're going to have n zeros. And then we're going to learn, once we learn some other ones, how that could be. So you could have, if I have a third degree polynomial, I could have at most 3 zeros. I could have less, but I had that the maximum I can have is 3. The graph of n has at most n minus 1 turning points. So turning points are these points here that I got circled where the curves turn. So those are the turning points. So one thing I can look at here is this has 1, 2, 3, 4 turning points. So that means that the smallest degree that this one could have would be 5. That is n had to be 5 or larger, but that'd be the smallest one because at most it has that many turning points. Okay, so the graph of n has at most n minus 1 turning points. Turning points are called, sometimes are referred to as your relative or local max points on your graph, or your relative minimums, or sometimes called local minimums. You notice on this graph here, this is a local max, and this is a local max, and this is a local min, and this is a local min. So turning points are your max and mins, local max and mins of the graph. All right, now this is where I'm going to talk about the different results that you get. So if I ask you to find the zeros of the function, you're going to write your answer as x equals some number, and you're going to solve that. So basically, you just set the function equal to 0 and solve for x's, and you write your answer as x equals 0. Now, if I ask you to find the solutions, well, I just said to solve the equation, it's going to be the same thing. X equals a number is going to be your solution. Now, if I ask you to find the factors of a polynomial, it's not going to be x equals a. It's going to be, you're going to take that x equals a and then get it set equal to 0. And then the factor is this left-hand side. So x minus a would be our factor of that polynomial. And if I ask you to find the x-intercept, by definition, x-intercept point in which the graph crosses the x-axis, that's going to be written as an order pair, a point where your x-coordinate is going to be a and your y-coordinate is 0, because in order to find all these, which are you're going to do the same process, you're going to set f of x equal to 0, so y is going to be 0. So just how we write the answer is going to be slightly different. Okay, now here's where the important thing about at most you have n real zeros. And the reason for that is some of your zeros can repeat. You can have repeating zeros. And what we call that is multiplicity. So a factor, if you have a factor, x minus a raised to some some power that's greater than 1, then you will have a repeating 0 at the factor x equals a, okay, of multiplicity k. Now, if k is an odd number, if this is raised to like, if I get like x minus 3 to the fourth, odd is first, so x minus k to the fifth power. Okay, if I have it repeating an odd amount of times, this affects the graph by that x-intercept. Well, your graph will go to that x-intercept and then it will cross it. It will cross the x-intercept. So it crosses the x-axis at x equals a. So I know on this graph at 1, 2, 3, I know my graph actually crosses this x-axis. So it starts down, crosses at 3, and continues up. So I got something going like that. And how it crosses, how it goes up, it might look like that, or it might look something like, it might approach it something like this and then curve like that. We'll see. That's what we have to figure out a little bit more. The main thing is it crosses across the x-axis. Now some functions might cross in this direction, but we know it's going to cross the x-axis if the multiplicity is odd. Now if the multiplicity is even, such in like 3 squared, okay, it will only touch. So it touches the x-axis but does not cross it. So it looks something like this. It kind of touches and bounces back. Or you can have something that looks like this, whatever value there. So it touches and then bounces back at that value that we're focusing on, that 0 that we're looking at. Okay, so even multiplicity touches the x-axis at that 0 or x-intercept, and odd multiplicity, it crosses the x-axis at that 0 or that x-intercept. So how can I get all this knowledge put together in a concrete problem? And that's what we're going to do here. And this is the best way to explain it, is just work through an example. So we have quite a few things we want to talk about. First, we're going to find the 0 of this polynomial. So remember when I talked about, I said finding the 0. To find the 0, all you do is replace f of x with 0. In finding the 0, finding the roots, finding the x-intercept, finding the solution, that all the same process. Y is 0. Okay, so it doesn't matter what term I use there, you're going to do the same thing. First step, replace the y with 0. Then you're going to solve this. I'm going to choose to solve by factoring. So I notice I have a GCF of, I'm going to take the negative out, negative 2x squared. And so that gives me an x squared here and a negative 1. And then I know that x squared minus 1 is the difference of squares. And so that'll factor to x minus 1 times x plus 1. And then now I use my 0 product rule. I set each of these factors equal to 0. And we solve. And I get x squared equals 0. So x equals 0. X equals 1. X equals negative 1. And those are my zeros of the polynomial. Since I asked you to find the zeros, x equals negative 1, 0, 1. Now you can write this at how I wrote it. You can write it as negative 1, 0, 1. Those are your zeros. And notice when you write your zeros like this, you always write it in increasing order. So that's my zeros on my polynomial. Now it asks you to describe the multiplicity. So notice here I had x squared. So I have a multiplicity of 2 because the x is raised to the second power on this one. So for B, x equals 0 has a multiplicity of 2. Now, what does that tell us? A multiplicity of 2 is an even. Remember, even tells us it's just going to touch the x-axis. Now, I put that here. That's not required in the problem. This is all that was required in the problem in this part B. But I put this touches here because that's going to help me later when I have to plot it, when I have to sketch the graph at the end. Okay, so I'll go ahead and gather that information. Part C. Let me change colors. It's getting kind of messy here. Okay, part C says determine the maximum number of turning points on the graph. All right, so my degree of my polynomial is 4 because that's the highest power. So that's my degree of my polynomial. So the number of turning points is equal to n minus 1. So 4 minus 1 is 3. So this is the maximum number of turning points for this graph. That's all you got to do, n minus 1. D, use the leading coefficient test to describe the end behaviors of the graph. So my leading term is negative 2x to the 4th. And so that is an even degree, and that is a negative coefficient. So it means even the same direction, and it's going to be in the negative direction. So the left end will be going toward negative infinity as x goes to infinity. I mean, x goes to negative infinity. I said left, didn't I? Like x goes to negative infinity. And the right side is also going down as x goes to infinity. So that would be my end behaviors of this graph. I'm running out of room, so I'll put E over here, and we'll do it in green. Okay, so E says, okay, we're going to find additional points to plot on the graph. Now, I have, so far, I have I have zeros of 0, 1, and negative 1. All right, so if I was plotting this, say if I plot my graph here, there's my x-axis and my y-axis here. All I know so far on my graph is I have an x-intercept or a 0 at negative 1, 0, and 1. Those are, I figured out those 3 points. And we got that in step 1 here, zeros. Zeros are the same as x-intercepts on our graph. So we know those points are going on. But I don't know what's happening between those points or after those points. So that's where you have to get additional knowledge. So everything you want to do, notice that I've kind of broken this up into 4 little intervals. I got a number, some x value less than our smallest x-intercept, and then number between the x-intercepts. There's 2 of those, and the number on the out. So all the additional points you need to do is you need to find some x value beyond and between every 0. So x value beyond and between every x-intercept, or 0, because they mean the same thing. So beyond the smallest x-intercept, I need something less than negative 1. So I'm going to choose negative 2. And then you substitute this into your original function. So our f of x is negative 2x, which is negative 2 in this case, to the 4th, plus 2 times negative 2 squared. And you just work that out, and I've already done it, and so I got negative 24. Then you need to find an x value between, so I need something between negative 1 and 0. So I'm going to choose negative 1/2, and I'm going to substitute that in my equation. And then again, you'll take some time to work this out. You can pause if you want to work it on your own. And I find that value was 3/8. And then something between 0 and 1. So I'm going to choose positive 1/2. And also got 3/8. And something beyond 1. So I'm going to choose 2 for simplicity. You can choose any number greater than 1. And you get 24. And now I have 4 points here. Negative 2, negative 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 20. Oh, perfect. Okay, so I'm going to count by 2s. I don't have to go all the way down, but it ends up here at the very end. So at negative 2 on the x-axis, I'm down to negative 24. And then positive 2 x-axis, I'm down to negative 24. And then at 1/2, I'm at 3/8, so just tad up here. just a tad up here. And notice that on my left end, my graph should be going down toward negative infinity. Yes, definitely going down toward negative infinity. And then my right end says my graph should be also going down to negative infinity. Yes, going down. And how did I guess I should undo that. And then how am I going to do these dots in between? Well, remember from our multiplicity here, it's only going to touch the graph at 0. So I know it just, undo. We touch our graph and then we go back up. So notice I'm just touching at 0. But at the other ones, they had just 1. So it crosses the x-intercepts there. It crosses the x-intercepts. And then our end behaviors are going down. And that's it. You sketch your graph. Clear up some room. And let's do one more. All right. So I'm going to do very similar on this one. All right. So for A, I want to find our multiplicity. We find our zeros. So I replace f of x with 0. Take out my GCF. This time when I take out my GCF, that leaves me with an x plus 3. And so I get negative 2x squared must be 0, or x plus 3 equals 0. So x squared equals 0, x equals 0, or x equals negative 3. So my zeros are negative 3 comma 0. Negative 3 and 0. B, find the multiplicity. Well, again, the 0 was repeated. So x equals 0 has multiplicity. You can abbreviate that. Multiplicity of 2. And since it's an even multiplicity, that tells me it's only going to touch the x-axis at that point and not cross it. But at negative 3, it's going to cross the x-axis. C, determine the maximum number of turning points. So our degree is 3. So 3 minus 1 gives 2. So we have 2 turning points. Maximum of turning points. So 2. So I have a max and a min on the graph. D, determine the end behaviors of the graph. So our degree is 3, which is an odd degree. Our leading coefficient is negative 2, which is negative. So it's going in opposite directions and ending at negative. So it's going to look like this. So that tells us f of x is going up as x goes to negative infinity. That's our left end. And our right end, f of x is going to negative infinity as x is going to infinity. And then last but not least, E. All right, so right now in my graph, I've gotten an x-intercept of 0 and negative 3. So I got 0, 1, 2, 3. And I know it touches at 0 and crosses at 3. And I also know that I have to be, my left end is up, so I know it's going to have to cross this way. And then it's going to have to touch this way so that I can end going down. So I got this information already from our end behaviors and using that. So now I just need to fill in more data into this graph. Let me erase those little marks so I can fill in that more data by finding other points. So I need something less than negative 3. So I'm going to choose f of negative 4. Plug that into my equation. And you get 32. Okay, and then something between negative 3 and 0. I chose negative 1. You can have chose something else. And I got negative 4. And then something greater than 0, I chose 1. And I got negative 8. All right, so I'm going to count by fives. 20, 25, 30, 35. Okay, so I need at -4, I'm all the way up here to 32. So just about here. Okay, and that makes sense because my end behavior on this end, I needed to be up, high up, or toward infinity, going toward infinity. So that did good. Now in between the two at -1, I'm down to -4. So since I'm counting by 5, that's about right there. And at 1, I'm down to -8, which is about here. And so now crossing this x-intercept, touching this x-intercept, in behavior down, in behavior up. There you go. That's all I need for your sketching of the graphs. All right, last thing we're going to learn is called the intermediate value theorem. So let A and B be real numbers such that A is always less than B. If f is a polynomial function such that the y value at A is not equal to the y value at B, or f of A is not equal to f of B, then the interval from A to B, including the endpoints, f takes on every value between A and B. So the intermediate value theorem says. So basically it's saying, if you get some x value here at A and x value at B, and our y value, this is our f of A, and then let's say over here is our f of B. So from here to here, well, there's my B. Okay, so from here to here, I have that value, okay? And so the intermediate value says, if it's a polynomial, it's continuous. And the only way I can get from a positive y value to a negative y value is somewhere in here, I got to cross the x-axis. And that means I have to have a 0 somewhere in there. So if x can be, so if you can find a value x equal a on the polynomial function that is positive, and another value of x equals b on the polynomial where it is negative. So if you switch from a positive to negative or negative to positive, doesn't matter which order, then you conclude that you must have at least 1 0. So somewhere I have to cross the x-axis. So that must be 1 0. Now I can only include that it must be at least 1 0 because it could have done from here to here. It could have gone something like this to get there, and I could have had multiple zeros. But at least I know I had to cross it at least once. And that's all the intermediate value that we're going to learn. If you go in calculus, you'll learn a little bit more. So now we're going to do this, but we're going to do this problem with the help aid of a calculator. So go ahead and get to your calculator and turn that on. And so in our calculator, we're going to go to our y equals. We're going to plug in this equation. So this is negative x to the fifth to the fifth. Okay. Plus 3x cubed minus 2x plus 2. And I'm just going to zoom standard, which is 6, and I'll get this graph. Now, I'm looking for the x-intercept, and I can kind of see on my graph that this is between 0 and 3. So I'm going to go to my table function. If you notice that that's second graph in our table function, and notice that if I move in between 0 and 3, notice I kind of switch from positive to negative. In fact, it switches between 1 and 2 is where I switch from positive to negative. And so that's important for me to see. So now I would just copy this information. So I'd make a table on my graph, on my paper, and say x equals 0, y is 2, 1, y is 2, 3 at 2, y is negative 10, at 3, y is negative 166. So I've narrowed it down between 1 and 2. So that therefore, by the intermediate value theorem, there must exist some 0 between 1 and 2. The only way I'm going to get to a y value of 2 to a y value of negative 10 is I have to cross 0 at some point. Then that's part A, okay? So that's all I got to say for part A. So for A here, I make my table. 0 is 2, 1 is 2, 2 is negative 10, 3 is negative 166. So this is where I switch. So because of the intermediate value theorem, there must be a 0 on the interval from 1 to 2. Okay, Then B says, okay, let's adjust this so I can get within the nearest hundred. So let's get closer than just between 1 and 2. Okay, so go to my graph again, my calculator again. And this time I'm going to go table set. You did find table set, you do second window. And then I want to start my graph at 1. But this time I'm not going to go straight to nearest 10th. I'm going to start at the nearest 10th. So let's delete that at 0.1. So I'm going to do it on stages and then just push table, so second graph. And notice here again, I'm looking at my y value is what I'm focused on. Where does it switch from positive to negative? So in between 0.6 and 0.7. So I'm going to go back to my table set. And this time I'm going to start at 0.6. So delete that. 0.6. And I'm going to count by what it required was the nearest hundredths. So that's 0.01. And then go back to my table. And then I'm looking at my y. Where does it switch over from here to here? It was in between an x at 1.64 and 1.65. So that is where I would write on my paper that it's on the interval from 1.64 to 1.65. Okay. And then C, we're going to find the exact 0. So we're going to find the exact value using our graphing calculator. So to find your exact value, you're going to go back to your graph this time. So I'm going to graph the function. So this is our graph. Now we're going to calculate our 0. So we're going to do second trace. That's our calculate. Notice example 2 is 0. So highlight that, push enter. And ask for left bound. So I need an x value to the left of that 0. So I'm just going to move my cursor until it gets close to that 0. So now you can see my little point there. It'll move close, but never pass it. So I got to stop there, push enter, and then move it past the 0. Push enter, enter again. And it tells us our 0 is 1.6463. And then your calculator might even go to more points, so 1.6463. My calculator actually went to more. Let's change our mode here. I think I have it rounding. No, it has it floating. Okay. And so that would be your 0 that you would put in. So 0 of 1.6463. And that's how you use the intermediate value theorem.